Hello and welcome to lecture 23 of Math 2R03. In today's lecture, we're going to spend some more time on section 8b. Now, last time we kind of spent a lot of time on the theory, and I'll restate the theorem that we proved last class. But the problem with what we did last class, it's not necessarily a problem, but one thing you don't actually see is actually how you compute some of the things that show up in the main theorem from last class. So in today's lecture, I really want to spend the whole time working out an example. And so this example is good because we'll see lots of the various pieces that we've learned in this chapter so far. So just to recap here, and I'll make myself disappear, is that last time we learned that if we take a linear operator, and if we assume that our coefficients are complex numbers, and let's say we also know what all the distinct eigenvalues are, and furthermore, we know what the multiplicity of each of the eigenvalues are. And just remember what that means is this is the dimension of the generalized eigenspace of the eigenvalue. Then we prove that there's a basis of V such that the associated matrix is a block diagonal matrix. So these are all square matrices on the diagonal. We have zeros off on the side. And each of these AIs is actually an upper triangular matrix where on the diagonal we have the ith eigenvalue, and up here are some possibly non-zero values. And this matrix right here is a di by di matrix. Okay, so that means that A1 is a D1 by D1 matrix with lambda 1s down the diagonals and something up on the upper right-hand side. Okay, so maybe I'll just put that here. So this is an upper triangular matrix. With lambda I on the diagonal. Okay, so this is the theorem that we proved last class, and it says that there is a basis, but how does one actually get their hands on their basis? Okay, now you can do this. You actually have all the tools that you would need from basically Math 1B03. There has little tweaks that maybe along the way you have to do, but most of the tools you already have from your first linear algebra class. But it's just the calculation becomes quite long. And so today what I want to do is do a worked out example to find this particular matrix. And the interesting thing is that the whole lecture for today is actually looking at this one particular example. Okay, so that's our goal for today. And our goal specifically is we're going to take this linear operator on C4, which takes the vector in C4, x1, x2, x3, x4, and maps it to this other element in C4. And what we want to do is find a basis of C4 so that when you figure out the associated matrix, it looks like a block diagonal matrix. Okay, so just to get us going, we'll start with looking at the standard basis of C4, and the point is from the standard basis of C4 we see that we're going to have to do some work because it doesn't have the right form, right? So the standard, the matrix associated to the standard basis would look like 10, 0, 0, 0, minus 7, 10, minus 4, 10, 15, 5, 25, and minus 5, and minus 2, minus 5, 1, and 25. So remember how you get this. The first column is what you get by plugging in the first standard basis. The second basis is what you get after you plug in the second column is what you get after you plug in the second standard basis, and so on. So that's the matrix you have. It definitely doesn't look like this form right here. And in fact, we're not even close to starting looking at this theorem because all we have so far is the t, the linear operator, and it's over the complex numbers. Excuse me. So now the next thing that we have to do is go off and find the eigenvalues. Okay. And oh, it looks like I had left myself room to write the matrix here. So C above. That was poor planning on my part. So the next thing that we need to do in order to do this theorem is we're going to need the eigenvalues and we need to compute the multiplicities. Okay. Now we could use the eigenvalues. We need the eigenvalues, so you can use the approach of Math 1B03. You could either do it by finding the characteristic equation, or you could do what I did, and you could just say use Octave or MATLAB. Okay. And I've actually cooked things up in this example that it's actually that there are two distinct eigenvalues. So the two distinct eigenvalues are lambda equals 10 and lambda equals 20. And what we know from section 8a and 8b is that our vector space V has the decomposition into direct sums as the generalized eigenspace of 10 plus the direct sum of the generalized eigenspace of 20. Okay, so that's what our vector space looks like. And so we're off to a start, but what we have so far is our t, and we have our lambdas. And so we'll pause here because the next thing that we have to do is we have to compute the multiplicity of each of these eigenvalues. And I should mention that at a lot of points, sometimes you may actually get stuck right here is finding the eigenvalues, because if your matrix is quite big, or sorry, if your linear operator is on a vector space that's quite big, the dimension-wise, then the characteristic polynomial approach won't work necessarily because you're getting a polynomial of large degree. So sometimes you know that such a thing exists, but you may not even get your hands on these particular eigenvalues. Okay, so we'll pause here, and when we'll come back, we'll still try to get all of our pieces for our hypothesis.